Hey guys, in this video we're going to be looking at Loci. Wait, is it Loci or locuses? You know, the plural of locus? I think it's Loci. Anyway, yeah, we're going to be looking at Loci in the complex plane. Now, if you haven't heard of a locus before, it's basically just the graph of an equation. Don't worry, it's all just fancy terminology, you'll get used to it. Let's start off with a very simple equation to begin with. Say we want to sketch the locus of all the complex numbers that have a real part equal to 3. So what we're trying to find is all the complex numbers which we'll call z that satisfy this equation. The real part of z is equal to 3. For example, our locus will include complex numbers such as 3 plus I, and 3 minus 7i, and 3 minus pi divided by the square root of 2 times I, because their real parts are all equal to 3. But what we really want to do is to sketch them in our complex plane. So let's draw it up and plot these points. Now 3 plus I is around here, 3 minus 7i is well down here, and 3 minus pi divided by the square root of 2 times I is give or take here. Now we can make up some more points like 3 plus 2i and 3 plus 0.01 times I and plot them here and here, but as you can see, all the points are going to lie on this line right here. And by sketching this line, we've sketched our locus. And that's it, we're done. However, plotting and connecting points up isn't always the most practical way of finding the locus. For one thing, how can we be sure if, for example, these points down here will always work without testing them? Now, obviously they do, but it won't always be as straightforward all the time, especially as we get to more complicated loci. We really need a better and more general method of finding the locus. So let's go back to our equation. The real part of z is equal to 3. Since z is a complex number, let's call z x plus iy. Now normally I would write a plus bi instead of x plus iy, but this time I'm going to use x and y, and you'll see why in a minute. So we have the real part of x plus iy is equal to 3, but the real part is just x. So that means x equals 3. Now I'm actually going to sketch the line x equals 3 in the Cartesian plane. And notice that the line x equals 3 perfectly matches our locus in the complex plane. That means that we can sketch the locus of z by pretending that the complex plane we're sketching it in is actually a Cartesian plane. And then we simply graph the equation x equals 3. And this will work every time, because if we go back to our complex plane, the real part of z, which is x, corresponds to how far across you go along the real axis. But that also corresponds with the x-axis in the Cartesian plane. And it's the same thing with the imaginary part of z. Y corresponds to how far up or down you go along the imaginary axis, which is exactly how the y-axis works in the Cartesian plane. This makes everything a lot simpler, because we know very well how to graph equations in the Cartesian plane, and so converting between the Cartesian and the complex plane to find the locus of a complex number makes things much easier. For example, let's try a not so simple locus problem. The problem we're going to do is as follows. Sketch the locus of the complex number z that satisfies the equation the conjugate of z times z plus 1 is equal to the modulus of z squared plus the imaginary part of z times 1 minus I. Whoa, now that's complex. We've got the conjugate of z, the modulus of z, and the imaginary part of z all packed into one equation. So clearly trying out points and then connecting them is not going to work like before. But have no fear, for I would never give an example that didn't turn out nice in the end. So letting z be equal to x plus iy means the conjugate of z is equal to x minus iy, and the imaginary part of z is going to be just y. But now what about the modulus of z squared? Well, hopefully you haven't forgotten that the modulus of z is equal to the square root of x squared plus y squared. So then the modulus of z squared is going to be equal to x squared plus y squared. Subbing all of these into our equation gives us x minus iy times x plus iy plus 1 is equal to x squared plus y squared plus y times 1 minus I. And now expanding all of this is going to give us x squared plus xiy plus x minus iyx minus I squared y squared minus iy, which is equal to x squared plus y times 1 minus I. Now we've got a few things that will cancel out here, such as this xiy and this negative iyx. These two x squares will cancel out, and this I squared will make this y squared positive, which will cancel out with this y squared. And now let's see what we've got left. We have x minus iy is equal to y minus iy. And again, these two iy's will go away. So we're just left with y equals x. Sometimes maths is beautiful. But we're not done yet. What does y equal x look like in the Cartesian plane? Well, it's just a straight line passing through the origin. And so that's it. That is the locus of our complex number, satisfying this horrific looking equation. Too easy. Now this method of letting the complex number z be equal to x plus iy will always work, but it can be quite long and annoying doing all the algebra. So there are a few special loci that you should be able to recognize directly, like the real part of z is equal to 3,1. We're going to need some more paper. The first two loci you should be able to recognize are loci of complex numbers that satisfy the equations the imaginary part of z is equal to a constant c, or the real part of z is equal to c. Now these two types of loci are simply straight lines, with this equation giving a horizontal line that crosses the imaginary axis at height c, and this one being a vertical line that crosses the real axis at c. Another loci you should be able to recognize is loci in the form the modulus of z is equal to a constant c. So if you think about this one, what it's simply saying is that the distance of the complex number from the origin is fixed. So that's just going to give us a circle centered around the origin with radius c. And yes, that is a circle, close enough. Another similar locus to that one is the equation the modulus of z minus z1 is equal to a constant c. So in this case, z1 is any given complex number. And now this locus isn't so obvious, but what it forms is a circle of radius c, but this time it is centered around the point z1 in the complex plane. For example, if we had the modulus of z minus 1 plus 2i is equal to 2, then we would have a circle with radius 2 that is centered around the point 1 plus 2i. So it would look something like this. Oh my god, that circle was atrocious. But you get the idea. Now you can take my word for it, but it's more fun to actually prove that that is what it is. Now I'm not going to do it because I don't have the time, but if you want a hint, try doing what we did before. Let z be equal to x plus iy and see what you can do from there. Anyway, more paper. Loci can also involve the arguments of complex numbers. For example, the loci of the complex number satisfying the equation the argument of z is equal to some angle theta is another type of locus you should be able to recognize. Now we can do this one just by using logic. What it's saying is that the angle that a complex number makes with the origin is fixed and equals theta. So this locus is just going to be a line that makes an angle of theta with the real axis. But be careful, because it's only 1/2 of a line, because the minute a complex number starts going below the real axis, then the argument of our complex number is actually this angle, and so it's not the same thing. Also, when the complex number is at the origin itself, its argument isn't even defined. This is because it could technically be facing any direction. It could be facing this way or that way, etc., etc. So we say that at the origin, a complex number has no argument, and so we have to put an open circle here so as to indicate that our locus does not include the origin. Another one that's closely related to this locus is the equation the argument of z minus z1 is equal to some angle theta, where again, z1 is just any given complex number. And just like our previous example before with the modulus locus, this locus is exactly the same as the previous one, except the line now starts at the point Z1 in the complex plane. Or in other words, it looks something like this. So for example, let's take the argument of Z minus 2 minus 4i is equal to 30 degrees. So this locus would be a line that starts at the point 2 minus 4i in the complex plane and rises at an angle of 30 degrees like this. Okay, that's it for this time, guys. Next time we'll be looking at these numbers called the complex roots of unity. See you then.